Alrighty. Hopefully this video goes well. Hello? I'm just a fellow mathematician. You could argue that. I'm going to be going over a differential equations problem. One that I think is kind of meaningful. Alright. I might just take a picture of this problem here, and then I'll put it on a little corner here so you can read it. But I'm going to read it out for you. So the problem states, testing, let me see. Okay. The problem states that by 10 p.m., a club of dimensions 30 feet by 50 feet by 10 feet is full of customers. Many of these customers smoke. So cigarette smoke containing 4% carbon monoxide is introduced to the room at a rate of 0.15 cubic feet per minute. Suppose that this rate does not vary significantly during the evening. Before 10 p.m., there's no trace of carbon monoxide in the club. The ventilators in the club mix the air inside and release this mixture to the outside at a rate of 1.5 cubic feet per minute. And so this problem essentially wants us to model a differential equation after this physical phenomena. It wants us to do so. It wants us to set up an initial value problem that describes the concentration of carbon monoxide at time t. It wants us to find a particular solution to the initial value problem, the IVP, and it also wants us to compute what would be the concentration of carbon monoxide inside of the room, the club. The concentration of carbon monoxide buildup inside of the club from 10 a.m. to 10 p.m. to 3 a.m. Because it's essentially telling us that a concentration of carbon monoxide greater than 0.012% is considered dangerous. I'm assuming that this is 0.012. I said 2%. I said 0.012%. What was I going to say? Yeah. A concentration of carbon monoxide greater than 0.012% is considered dangerous. And what I wanted to say is that I'm assuming that this is per cubic feet. Not for the entire room. Okay, so yeah, let's start tackling this problem. The first part, just warning, this is gonna take a while. These types of problems do take a while to, it's a differential equations problem. Yeah. So first part is we're just gonna establish what are the numbers that we know. Okay. So let's go about doing that. Okay. Alright. So we know that the dimensions of the club are 30 feet by 50 feet by 10 feet. Hence, the volume, the total volume of the room is going to be 15,000 feet cube. That is the volume of the total room. Okay, let me draw a little drawing here. These are 30, 50, 10. Okay. So that's what we're working with. Let me do a little temporary drawing of the setup here. Okay. All right, so this would be 30. This would be 50. This would be 10. 50 long, 30 wide, and 10 tall. All right, so what is the next fact we know? Okay, we know that the full thing is, let's just assuming that the full thing is filled with people that smoke. Okay, and that they're generating. Okay, they are generating smoke. They're generating smoke at a rate of 0.15 cubic feet per minute. 4% of that, which is carbon monoxide. Okay, so let's put it in our corner of facts. Okay. All right. 0.15 feet cube per minute. Okay. Smoke generated. Okay. Then over here we're going to be like, okay, 4% of which is carbon monoxide. Okay. Is that apparent in the thing? Yes. Okay. All right, so we have a rate of 0.15 feet cube per minute. 4% of the smoke that's being generated being carbon monoxide. Okay. So just imagine that within this club, smoke is being generated from the inside, and a portion of that smoke being carbon monoxide. Okay. So let me just draw people here smoking. Okay. Here we go. Okay. And as they're smoking, the club is getting filled up with smoke. Okay. How's the recording doing? Okay. Now. Okay. So now we have an output. We have ventilators in the club that are mixing the air inside So this essentially allows us to assume that, let me just finish the entire sentence here. So there's ventilators inside the club that mix the air inside and release this mixture to the outside at a rate of 1.5 cubic feet per minute. Okay. All right. So what I wanted to say is that this phrase here is very important. The ventilators in the club mix the air inside. So we're assuming that the mixture that's being output is an even distribution of the smoke that's being generated. You know, that like by the time the smoke is being output, it's not like there's like a lot of clumps of smoke over here and like not a lot of clumps of smoke over here. When the smoke is being output, we are assuming that the air is well mixed and that there's an even amount of smoke on the entire room. Okay. So let's write this. Okay, so we have an output air mixture of 1.5 feet cube per minute. Okay. So, yeah. So here, the important part of this rate here is that 1.5 only describes only describes the flow of air that's coming out. The mixture aspect of it, the mixture, the way we have this rate actually resemble the output of air mixture is we have to include the function which defines, the function that expresses the amount, the percentage of air within the room that is contaminated. Okay. Yeah, because if you think about it, in the beginning, there's not going to be a lot of air. There's not going to be a lot of smoke. But as time increases, the density of the smoke inside of the room will increase. Will obviously increase. People will smoke more, and the more they smoke, the more they will generate. Okay. So we're going to modify this rate here. Okay. We're going to say 1.5 times A of T. We don't know what A of T is. We don't know the function that describes the percentage of air, the percentage of contaminated air as time passes. We don't know that function yet. But we need it in order to be able to say here that the output of air that is mixed is, in order to say that the rate at which this air is coming out is in relation to the amount of air that's also contaminated, and thus a mixture. Okay. So, all right. So those are our general data that we have so far. Just for funsies, I'm going to draw here like a little pipe. Okay. And that pipe is releasing some of the mixture of air inside of the club at a rate of 1.5. Okay. take a look at that graph one more time if you really like it. It looks kind of like a lot of crazy stuff, but I'm going to erase it. 3, 2, 1. Now we're going to set up the differential equation. All right. The reason we set up a differential equation for this problem is because we're dealing with rates of change. Okay? You know, we're dealing with rates of change. Things are changing. So again, as I've expressed here, A of t represents the function that describes the concentration of carbon monoxide at time t. Although in the paper, if I've shown you the screenshot, the paper has c of t, but using c as a function name is a bit confusing because we're going to have constants as we unravel the differential equation. We're going to have constants that c. That are just named c, and so we don't want to confuse the two. I'm going to call this equation a of t. Okay, but we're working with the derivative of a of t. Okay, the derivative of a of t. This represents the change in concentration of the carbon monoxide as time passes. Is that obvious? dA of dt. All right? All right. So, first things first, we have the smoke that's being generated. Its rate, cubic feet per minute. 0.15, okay, 4% of which is carbon monoxide. I hope you understand why I put it 0.04, because when you change from 4% to the number equivalent, you would say 0.04. Okay. We divided this expression right here by the volume of the room. Okay. There we go. Now we're taking the entire room into consideration. Well, this is the input. This is the input. Now the output, we put a negative because the air is coming out. It's coming out of the room. It's being released out. So the output air mixture is right here. 1.5 A of T, okay, the concentration of carbon monoxide at time T. We're going to say A, okay. This number over the volume of the room, because again, this is in relation to the entire room. Okay. And we've set up our differential equation. Okay, we have an equation which contains derivatives of its own equation, which is that's what a differential equation is. Yeah, it's pretty crazy, but that's how you talk about things that are changing respects to each other. It's pretty interesting. Where am I on time? It's 20%. No. 20 minutes. Alrighty. So now we're going to clean up this function a little bit. We're going to clean it up. I like to abbreviate all my numbers and digits with scientific notation, because sometimes you get a lot of very small numbers. So I like to do scientific notation. So over here we have 0.15 times 0.04 over 1500. 15,000. Okay. And we get 4 times 10 to the negative 7. That's a really small number. So I'm going to abbreviate this with scientific notation as 4e to the negative 7. I'm going to put parentheses around it because calculators, this one at least, if I don't put the parentheses on my scientific notation numbers, it might get confused, you know. So just keep the parentheses just to make sure that this is an entire number. That's a unit. Now we do 1.5 over 1500, 15,000, which is equal to 1 e to the 4. So 1 times 10 to the negative 4th power, abbreviated as 1 e to the negative 4, scientific notation. Hit a parentheses, bring down the a, and this is the cleaned up version of our differential equation. So the first part of the problem states write an initial value problem that describes the concentration of carbon monoxide, C of t, at time t. Okay, so we haven't got there yet. We have to work with this differential equation for a little bit, but the first part with an IVP problem is that you define, you know, the original function, not the derivative, the original function at time 0, at input 0, what do you get? And our paper here says that before 10 p.m., there's no trace of carbon monoxide in the club. So that means that A of 0, okay, is equal to 0. This is our initial condition here. So at time 0, whenever no time has elapsed, at 10 p.m., the start of the counter, the start of the clock of this equation, it tells us that the concentration of carbon monoxide inside the room is 0. No people have started smoking yet at this time. Okay. All right. This is our initial condition. We've done the first part of the A part of this problem. About 25 minutes. All right. So now what we want to do is have this function solved for A. So we can then work on the initial value problem. Okay, so we see here we have dA over dt, so the derivative of A is equal to this function here, this expression. So the first thing we're going to do is a little bit of calculus, a little bit of algebra, calculus. We're going to move this d of t from here and move it over there. Okay. We move this d of t to this side by dividing, by multiplying it out. So you multiply the dt, it cancels out. We leave the dA alone. It goes to the other side, and we multiply by this entire expression. Put a parentheses on it. Just be sure to state that it's multiplying on the two parts of the expression. Now we want to bring this part of the expression that holds that A to this side, so we divide this out. Okay, I hope that makes sense. That is simple algebra. Okay, we've isolated dt by dividing this whole expression on both sides. This expression over the same expression is just equal to 1. We isolate the dt and we've divided it to the other side to get this output here. Now we integrate both sides. Okay. Here, in order to unravel this integral, we have to do use substitution. So we take this entire expression here, this bottom part, u, 4e to the negative 7, 1e to the negative 4a. We take the derivative of this expression, and when we take the derivative, because this is a constant, it becomes 0, and if we assume that this a is a variable, when we take its derivative, we are left with the number in front of it, because there's no power, so a to the 1, bring the 1 over, multiply this coefficient by the exponentiation factor of the variable, and then decrease the degree of the variable. Because we're left with a0 afterwards, we do not include the variable. It disappears. After that, we include dA to state that we have taken a derivative of this expression. We look at the derivative and we look at the integral. And we see that we have this dA, but there is no constant, so we divide the constant out of there. We're left with just dA. And now we do the U substitution. dA goes away. Say du. Okay. That is invisible on the yep. Okay, so this is our simplified integral. We can integrate this side pretty easily. So the integral of 1 over u du is equal to ln of u. So let me go ahead and write that over here. Okay, we make sure to bring the constant, this constant. Nothing happens to it because it's outside of the integral. But inside the integral, when we integrate this, it turns into ln, absolute value of u. U being this expression here. We substitute u again back to the original expression. Okay. And now the integral of dt is just t. Ready? Is that visible on the video? Yep. Okay. Now we have to do a little bit of algebra to isolate that a. Okay. Okay, so now we multiply both sides of this expression by negative 1e to the power of negative 4. So if we multiply this side by this number, this fraction will cancel out. So we can write ln 4e negative 7 on e negative 4a. We multiply this side by this number. Okay. Okay. And now, in order to unravel the ln natural logarithm, we take the Euler's number on both sides. And that unravels this side here. Euler's. Oh man, if there's any math people here and I've said Euler wrong, it's Euler or something like that. I'm still learning. I think it's Euler. or Euler. I don't know. Okay. E to the power of negative 1e to the negative 4th t. Okay. You just have a little bit more algebra to go. We take this number here, and we subtract it on both sides to get rid of it over here. Okay. That way we could just be left with 1e to the power 1e to the negative 4 a e negative 1 e to the negative 4 t. Something I missed is that when you take the integral of one of the sides, you got to make sure to include your c, your constant c, because it was an indefinite integral. Okay, you bring it down. All right. When you solve an indefinite integral, you have to make sure to include the constant that comes afterwards, c. And now, what do we do? Oh yeah. This number here, we had subtracted it out of this side. We're going to put it over here. Negative 4e to the negative 7. Is that noticeable? Yeah. Okay. And lastly, in order to isolate our a, we divide this out. Okay. That cancels out here. Cancels out there. And then all right. Now we've isolated. Remember, this variable here, this stands in for a of t. Okay, so we've essentially isolated the function itself to mean this expression here. So let me clean up the board real quick. Okay, rewrite it and clean it up a little bit. So a of t is equal to, okay, so I hope that you see this c here. I'll rewrite it again, make sure it's more apparent. We have e to the power of 1 e to the negative 4th plus c. So this entire thing is the exponent, Euler's number. Then we have minus, we come back down, we have minus 4e to the negative 7. Okay. Negative 1e to the negative 4th power. And get 40 minutes. Okay, so that c right there, we can this exponent here, we can simplify it. So let me isolate it out here, just to emphasize what I'm talking about. So this is equal to algebra exponentiation rules. This expression is equal to that. And because this is an unknown constant, that is a product of an indefinite integral that we took a couple steps back. This could be any number. Any number times a number is any number. Okay. So as we say, if we toss the constants, any constant, okay, Euler's number, that is a constant. We toss any constants into the C. Okay. And then, okay. So now we have e to the power negative 1, e to the negative 4th times c. And we can simply say that c e negative 1 e to the negative 4th. We can simply say this here. Okay, so we're going to modify this. Not going to modify, it's the same thing, but we're just going to change this expression to this. Okay. So we're going to say c e to the negative 1e4 minus 4e7. I think that's what it was. Yep. Yep. Okay. All right. So now we've done part A of this problem, where we wrote the initial value problem that describes the concentration of carbon monoxide C of T at time T. This right here, this is the general solution to the differential equation. This is the general solution to the differential equation that we had started with. So now for part B, we need to find the particular solution to the initial value problem. Okay, because as you see here, we have a C there. We need to see what constant would this need to be in order to satisfy this condition. Okay, so let's do some algebra, shall we? All right, so we set the function to 0, right? We have c e negative 1 e to the 4th. I forgot to bring the t. Okay. Yeah. I hope that the differential, no, the function we ended up here had a t up here. Man, gets exhausting just carrying over all these things, you know. But yeah, this is our independent variable. Okay. Okay, so now, is that it? That was it? Yeah, okay. So, what would, okay, so, so t, our value of t is equal to 0, so let's do that. Okay. Now, when you multiply something by 0, you get 0. And e to the power 0 is equal to 1. Okay. So now, in order to get 0, what would z need to be? Well, we have a, let's make it very explicit. If we multiply this bottom portion of the fraction out, okay, that cancels out. A number times 0 is 0. Okay. Let's clean this up a little bit. Okay. What c needs to be in order for this expression to be 0? Well, c needs to be 4e to the 7. Okay, so let's see if this is true. 4e to the negative 7 times 1 is 4e to the negative 7. And 4e to the negative 7 minus 4e to the negative 7 is 0. Okay. So our particular solution will be a of t is equal to 4e to the negative 7 e to the power of 1 e to the negative 4 t minus 4e to the negative 7 over negative 1 e to the negative 4. This is our particular solution. Okay? As you've seen, we started with the differential equation. That thing had many solutions. And we figured out a particular solution to model this specific scenario with this specific initial value condition. So that is part B of this problem. Now part C. A concentration of carbon monoxide greater than 0.012% is considered dangerous. Knowing that the club closes at 3 a.m., is it safe to stay until closing? All right, so now what we're looking for here is a number to plug into here. Okay. And we're looking for the amount of time in minutes that has passed from 10 p.m. to 3 a.m. Okay. So from 10 p.m. to 3 p.m. we have 10, 11, 12, 1, 2, and 3. 10, you never count the first one. So like 10, 11, 12, 1, 2, 3. 5 hours. 5 hours have elapsed. And how many minutes are there in 5 hours? Okay, so we know that for every hour there are 60 minutes. So for 5 hours we'd have to say 5 times 60, which is equal to 300 minutes. Okay. t is equal to 300 minutes. We have the proper units of time to input into this function, because this function is in terms of minutes. Okay. So now we're going to plug in t into this function to see what we get. So a 300, okay, is equal 4 e to the negative 7 e to the power of 1 e to the negative 4th is 300 minus 4 e to the negative 7 over 1 e to the negative 4th. Okay. Alrighty. Now I'm going to use my calculator for this. Right? Yeah, there we go. Wonder if I can plug this stuff in. Well, nah. Yeah. Alrighty, so you know what? Yeah, I'm gonna try and do it. Yep, here it is. Okay, so all right, so I'd say first copy this function down. That one right there. That's where we're going to be plugging into the calculator. Okay. So here we're going to start out with this guy. We're going to do 4 e to negative 7 Euler's number to the power of parentheses 1. Oh man, keep on messing up. Okay, remember that negative sign here? We got to bring it down. Okay, that negative sign comes down here. Please, there you go. That's all. The negative sign. We can't forget about our negative signs. Okay. There we go. Go back over here. Okay. So we do like negative 1 e to the negative 4. Is this even visible? I don't know. Hopefully it is. Then we're going to do 300 here. Then we do 4e, negative 7. And then we're going to do negative 1e to the negative 4. Okay. What do we get? Wait a second. Wait, do this again. Alrighty, this is the number that we get. Is this visible on here? Wait, was I shadowing this thing? Oh, yeah. Well, that's visible because I can see it. That is the number that we get. Alright, so if a of 300 minutes, the function is equal to 0, 0, 0, 0, 1, 1, 8, 2, 18. Okay, so let's interpret this. So in the beginning, we had converted 4% to 0.04. Okay. So this is not a percentage yet. This is close. In order to get into a percentage, we have to just take this number and multiply it times 100. Okay. Let's see what we get now. So this number multiplied times 100 is equal to 0.011821787. And now we can say that this is That's a percentage. Okay, so, all right, let's go back to our little problem here. So it says that the concentration of carbon monoxide greater than 0.012% considered dangerous. Knowing that the club closes at 3 a.m., is it safe to stay until closing? Okay, so they're telling us that at 0.012%, that's considered a dangerous amount of carbon monoxide. I'm assuming that this problem is saying per cubic feet. So here in this problem, we have 0.0118, okay, which is just slightly below that threshold of 0.012%. You know, as an engineer, I would say that there's not enough tolerance in there to call it safe. You know, you can easily round this up. You can easily say like, oh, like, okay, right? You can round up that 8. That 1 here, you can round it up to 0.012%. So yeah, you know, I think that mathematically speaking, it is below 0.012%. You know, as we know, they're in the real world, right? I mean, things are kind of weird in the real world, right? I mean, things are going to fluctuate. This model doesn't account for all of the little nuances that happen, you know. It rather predicts what's going to happen in a more simplistic manner. I would say that if I was writing a regulation if I was writing a regulation saying whether it would be allowed to have people this long inside of the club, I would say that no. I would say that that no, people shouldn't be allowed to stay in there for that long with that rate of smoke, that rate of carbon monoxide. You know, with these levels of carbon monoxide after that time, no, I wouldn't allow people. I wouldn't, you know, I wouldn't sign off on that. Yeah. You know, like for me to sign off on something like that, I'd have to see that after doing this entire calculation, it took so much time. Like the tolerance is much greater. So 0.012% being the threshold. Like I would have liked to see, I don't know, 0.001%. You know, that would have been much more tolerable, or perhaps 0.0001%. You know. So you know, at this point, this could be turned into a more of an engineering problem. We could experiment with the amount of output air mixture that would be required in order to minimize this percentage down, bring it down. We could think about the amount of inflow air of new air, with respect to output air, to further minimize the percentage here, like that. That's how you would turn it into like an engineering problem, right? Yeah. Other than that, I mean, that is the solution to this problem. It's been an hour and 30 something seconds, so I'm gonna call it a day. Yeah, there you go. If you stayed this far, then perhaps you might want to leave a like and subscribe. Yep. Okay.